All right, good morning, good afternoon, everyone. So I'll be discussing some of my most recent work related to an adaptive tribal topology for implementation with a particle swarm optimization. So this is a presentation to be presented at CSCE 2020 on July 27th. Presentation overview, we'll start with just a basic background and overview of the problem, our methodology and novelty that we add with our paper and results. Then we have the results and discussion of our work, followed by the conclusions and future work. So problem overview, we start with optimization. So optimization, as it generally is considered, is a problem where we have an evaluation of one or more objective functions, and the problem is usually constrained to a certain space, and there's certain limitations placed on the problem. As an example, at the top right, what we have is a continuous type optimization problem where we have usually a global minima or maxima that you're trying to solve for, and this solution space is usually scattered with various other local minima. Another problem is the traveling salesman problem, which is shown actually in the bottom right. So those blue dots that we see correspond to all the city positions in Canada, and there's 4,600 of them. And to the right of that, what we see is the city distance, an unoptimized city distance of the country of Rwanda. So in the field of optimization, the traveling salesman problem is considered a NP-hard problem because the problem cannot be solved in polynomial time. So what we try to do is we try to utilize various evolutionary algorithms and other heuristics in order to approximate a global minima or maxima to these problems. And for our work, we're implementing our heuristic and evolutionary algorithm as particle swarm optimization. So in particle swarm optimization, we initialize a set of particles in solution space, and we each coordinate the particles to explore the solution space. So we call this manner exploration of the solution space. While at the same time as the particles explore, we want them to exploit certain local minima that they found in the eventuality that they find the global maxima or minima. So on the very right, what we have is a figure of a particle x sub I that's initialized, and it's being influenced by its velocity and inertia being shown by omega, while at the same time it's being influenced by its c personal, which is its personal best that it's found, optimization objective function that's found, and C sub swarm, which is the best found by the swarm and all particles as a whole. So in particle swarm optimization, we sort of have that careful balance that we're trying to balance the exploration and exploitation, and we do this by managing these personal, social, and swarm influences. So to this plot that we have is some of our recent work where we have a high inertial coefficient corresponding to each particle exploring on its own, and as we go on, we dampen this value and we increase the values for the personal and swarm coefficient so that we can exploit various personal bests that have been found. So one of the shortfalls of particle swarm optimization is that it's very parameter specific, and there's many parameters to initialize. And as a result, when it comes to one problem to the next, we have to carefully tune these parameters to the problem at hand. So the particle swarm optimization, as it's generally sought, is not very generalizable, and that is one of the major shortfalls. So as part of our novelty that we add, we want to introduce a tribal topology. So how this works is that we remove all aspect of a global influence, that is to say the particles being familiar with a global best by all particles, and what we do is that we initialize them into separate tribes and only have them relate to what the best that the tribe has found as the C sub swarm. So now it's C sub tribe, and this is similar to how we can relate it to how human populations have historically behaved, where we were looking for let's just say a body of water or a food source, and we separate tribes into populations, and then the information related to where the best food or water source is sent throughout the tribe as a form of feedback. So our implementation, we also want to dynamically manage the population size by looking at tribes that perform better and encouraging them by spawning new members, while at the same time, larger tribes, for example, that are performing poorly, we can have them die off over time. And we do this through the evaluation of a fitness parameter. So in this short video, we just have initializing a set of particles that are all traversing the solution space and finding the global minima for the Schwefel function. And as you can see, they just quickly converge to the top right, and all the tribes were corresponding with each other until the final solution was found. So with our fitness evaluation, we developed the equation on the top right that's going to manage this for us. So F sub I is the current fitness of the particle I for the next time step. And what we have here, we have three parameters. We have S sub S, velocity, and C sub T and C sub T. So S sub S is the normalized fitness of the tribe. This parameter just takes into account that if a particle exists as part of a larger tribe with a large fitness, it's going to be penalized more because of the 1 minus S sub S, as opposed to small particles will have a smaller normalized fitness relative to the other tribes, and therefore this will evaluate to be smaller. Additionally, we have the velocity of the particle, which just says that from time step t to t plus 1, how much it traverses in the solution space. So we want to penalize tribes that are moving more, and we can sort of conceptualize this as if they're using more fitness or more energy. And additionally, we want to take into account not just how much they move, but whether or not solutions are being found. So we do this through the evaluation of the absolute value of C sub t plus 1 minus C sub t. So from one iteration to the next, is there an improvement or maybe not an improvement in the objective function evaluation? So we want to penalize more, or we want to increase the fitness for those values which are finding new solutions better or worse, and consider them to be more of a penalty. And this is important because if we find particles that are have a low velocity and are not finding better objective function evaluations, they'll have very low fitnesses. When a particle has a low enough fitness, it'll be killed off. So this takes those parameters into account. And like I said, as larger tribes are promoted and they spawn new particles, if some of the members perform poorly, they're killed off. So the spawn behavior is very important and is at the essence of what we aim to implement. So what we have is we have a parameter called F sub I cumulative. So this is for each particle, it accumulates the fitness over time according to the equation in the prior slide. So what we do is in each iteration we compare it to a value called tau spawn. So what this says is if the cumulative fitness is high enough, so it's finding better solutions, it's moving around more, and it's larger than tau spawn, what we're going to do is we can spawn a new particle based off of the other members of the population. Alternatively, if we find that the particles are finding little to no improvement in solutions, so that absolute value C sub t plus 1 minus C sub t evaluates to close to 0, then it's very obvious that that particle may be stuck in a local minima. If it has a low velocity, then that means it has an inability to escape those local minima. So therefore, the cumulative fitness will evaluate to be smaller. So what we can do is we compare it to a value, t sub kill value, and if t sub kill is larger, then we can delete that particle. And of course, one of the interesting things that we need to know is how can we manage the t sub spawn, t sub kill values, and we do so dynamically depending on the current size of the population. So we have this constriction coefficient that we use, which is used to manage these values for tau. So the idea behind this is if we look at the plot, all these values converge above when the number of swarm members capital S is 5. This says that if we initialize the particles so that there's 5 particles in the population, as the population size grows to be above 5, we want to sort of create influences that will restrict it to be closer to 5. And conversely, if we want if the number of particle members becomes less than 5, so they're killed off, so there's 3 for example, then we want to promote the value of tau spawn and reduce the influence of tau kill so that particles are spawned more frequently and they're killed off less frequently to manage the population close to that initializing value S. So as I said, larger deviations from the starting population will change how much the value for those taus change. And also we implement the value for a value sigma, and this value sigma is used in the equation found in the plot space, which just manages the slope at which these values change. So a lower sigma will have a greater change, and a higher sigma will have a lower change. So those are inversely proportional. So for our work, as we want to test it against a series of continuous benchmark problems. So we want to implement a tribal topology to test against a very a subset of different benchmark problems where the local minimas are of different frequency, they're found at different locations, and more importantly, the depths are different. So it would encourage particles to perhaps get trapped in local minima, and therefore we could kill them off as if required. So the 4 benchmark functions are the Langer, Schwefel, Holder, and egg holder functions. So some of the results of our topology, these numbers shown below the Langer, Schwefel, Holder, and egg holder refer to the fraction completions where the global minima maxima were found, averaged over n equals 30 iterations. So just to show that the regulation coefficient, for example, when we increase it, the regulation coefficient or the sigma, as that increases, it has less of an effect on tau kill and tau spawn. So what this says is, for the Schwefel function, it found the global minima maxima 100% of the time, but in the egg holder function, for example, it went from 0.69, 0.62 down to 0.6. So we actually, in that case, for that function, would want a lower regulation coefficient. That means to say the population size changes much more drastically. And this was not the case for the Langmuir, for example. So these parameters are even then are very specific to the type of benchmark problem. The total population is something that we'd find to be consistent with our prior intuitions, which is when we increase the size of the population, we are more likely to find the global minima or maxima. And finally, the tribe number D just goes to show that depending on the problem, at least with these 4 benchmark problems, as we increase the number of tribes from 3 to 7, more tribes means that the amount of information and the exploration is dispersed. But we actually found that when we increase it, say to 7 for these problems, that we actually found poor approximations of the global minima or maxima. So what these 2 plots are showing is, one on the left shows a sigma of 2 for one of the benchmark problems, and the plot on the right shows a sigma of 5. So again, a sigma of 2 corresponds to larger changes to the value of tau kill, tau spawn, and promoting changes in population. So with the subplot on the left, what you see is that at the very bottom left, with the figure C, what you see is that the count for the number for each tribe changes quite drastically. So at some points, the tribe 1, which corresponds to the red plot, actually is driven to 0 at a time and then recovers, while the other populations for the other tribes change quite drastically. And we can see this directly on the right, where we see the coefficient values changing. So those are values for the tau kill and tau spawn. So they're changing as the population changes from its starting value. If we look at sigma 5 on the right, we can see that when we initialize the number of particles as count, we can see that the tribes change a bit at the beginning, but they approach a consistent value of somewhere between 2 and 3 for each tribe. And similarly, if we look at the tau for tau kill, tau spawn, we see that those values change for a bit during the initial iterations, but they remain steady as the problem progresses. And this is all dynamically managed, and this all relates to how the particles are moving in solution space, and how they're and while they're getting trapped in local minima or exploring, what the effect is. And additionally, we can also look at, if we were to leave that regulation coefficient to be constant, so say a sigma value of 2, we can look at both the holder and the egg holder benchmark functions. So these are the same values of sigma. So if you look at the very bottom left, what we can see is that initially the count of the particles in each tribe changes quite drastically with tribe 4, for example, being driven to 0, so the tribe itself is being killed off. But it steadily approaches a value where 3 of the tribes remain consistent in their number of population. And directly to the right, we can see the value of T kill, T spawn. We can see that those values increase throughout the iteration as required. We can compare this right to on the right to the egg holder function, where again with the same value of sigma, the population needed to change quite drastically as the problem progressed. And we can see this in the kill spawn and kill, the tau kill and tau spawn values, which change drastically as the population changes. And we can see that how that works out. So conclusions of future work. So we just introduced that our novel tribal topology was shown to successfully calculate a value of what we considered called fitness. And we used it by utilizing these spawn coefficients, being tau kill and tau spawn, which regulated the number of particles as the problem progressed and as the particles found local minima and global local minima and got stuck in there, they were killed off as required. So we also found that depending on the problem, the tribe members can be dynamically managed, and we don't need to tune those parameters. So if we initialize the number of particles in a population size of 5 to a set value, we can allow them to jump up to 7 or go down to 3 as the problem requires. And we also reduced the number of parameters required for the whole problem of particles from optimization down to the number of tribes, D, and the regulation coefficient, sigma. So those are the 2 number parameters that we need to consider. So for future work, we want to expand the work on randomly generated benchmark functions so that we can, rather than manually doing it, we can generate a set of benchmark functions with different local minima and just compare them directly. And additionally, we want to eliminate the reliance on parameter setting altogether. The idea being is that if you remove all parameter setting and we find an algorithm that is generalizable, then it'll become a one-size-fit-all algorithm. And with that, I'll take your questions.